currently a postdoctoral fellow at California University. And today I am going to talk about a problem that affects the very foundation of intelligent transportation, that is real-time vehicle-to-everything security. This work is in collaboration with Dr. Hussein Ali from University of Cambridge and Dr. 2.0 from NTNU. In this work, our paper introduces a novel blockchain consensus protocol called PoAh 2.0, Advanced PoAh 2.0, which is the acronym of Proof of Authentication version 2, enhanced by H large language model, that is LLM, which brings contextual awareness to the edge of the network. And why is it important? Imagine your car needs to brake immediately because a vehicle ahead has stopped unexpectedly. If this message is delayed or blocked or spoofed, lives are at stake. So our goal is to secure such communications without slowing them down. Now let's begin with the problem. Understand the problem that we are trying to solve. V2X, that is vehicle to everything networks, involve vehicles, roadside units, and infrastructure, all exchanging data under tight timing and safety constraints. Current blockchain solutions like proof of work are too slow. Another consensus like proof of stake assumes stable node identities, which is not realistic when vehicles are continuously joining and leaving the area. More critically, today all data is treated equally, whether it's a low priority weather update or urgent emergency braking command. Both follow the same cryptographic path. That's like sending a postcard and a hard transfer instruction through regular email. It just doesn't work. So we need a context-aware, latency-sensitive authentication system that adapts security based on the type of transaction while preserving privacy and decentralization. Our key contributions are: first, introduction of advanced proof of authentication 2.0, that is a lightweight blockchain consensus with adaptive authentication for vehicle to everything network, along with LLM integration for real-time context classification of vehicular data. Imagine it as ChatGPT for a car that is deciding if a message is a routine or life-threatening. Secondly, hybrid AI classification. It is nothing but when edge LLM is combined with random forest classifier for a comprehensive transaction sensitivity assessment. This approach complements the LLM's context classification with random forest classifying numeric metadata like speed or GPS. And also another one is three-tier authentication, which is divided in three categories like critical, sensitive, and normal messages. And different kind of messages follow different validation paths. We also provide here formal proofs that demonstrate security against Sybil, replay, and 1% attacks. This is among the first works to integrate LLMs into blockchain-based vehicle-to-everything authentication. The full system architecture. Let's say a car broadcasts an emergency brake alert. At the edge node, which could be the car's onboard unit or roadside device, the edge LLM interprets that message. It detects this message as a critical because it mentions phrases like immediate stop or collision risk or braking anomaly, something like this. Meanwhile, a random forest model reads the GPS, speed, vehicle density, and after analyzing all these things, after checking all these values, say it sees 120 kilometers per hour in a congested zone. So then it confirms high urgency. Now, instead of routing this through standard blockchain consensus, advanced proof of authentication consensus assigns high-level multi-signature authentication for this particular message, ensuring multiple trusted nodes validate it before the broadcast. But if it were a routine navigation update, then it will go through lightweight local validation, saving time and bandwidth. This architecture that you can see here makes the system intelligent, selective, and fast. Let's dive into the block design. Each advanced authentication block has three parts: block header, block data, and security information. And inside the block header, another important part is metadata. So inside header, as you can see, the timestamp, vehicle ID, sensitivity level like say normal, sensitive, and critical. These are the different levels. And with that AI confidence code, this is also playing a very crucial role. We need to understand how this code is coming. So this code is actually produced by combining the context classification probability from the LLM, that is how confident the LLM is about a particular message, whether it belongs to a certain critical or sensitive or non-class, and the feature-based classification probability that we are getting from random forest model, that is based on metadata such as speed, location, vehicle density, heading, so all these things. So one is coming from the LLM, another one is coming from the random forest. So we take a weight combination of these two sources and compute the final AI confidence score. Now, whether this score is important or not, we have to understand this. So this particular score is embedded in the block header and enables other vehicles and relators to interpret it just not like a message content, but it's a system's confidence on that particular message. If the confidence score is high, critical messages will be prioritized and will flow through the strongest validation path. And if the confidence is low or uncertain, the message can be either delayed or sent for further verification. Another part of this block structure is block data. All vehicular messages from lane changes to diagnostics, so like all messages are getting stored in the block data. So, for example, when a car detects black ice on the road and it generates a hazard alert, so it will have the information of location, time, sensitivity classification. Say AI confidence score is coming 92%. That means it is detecting the particular hazard as a real ice hazard. So this allows vehicles to trust and respond rapidly. And finally, another one is security section, where digital signatures, public keys, validator IDs, so all those things are preserved. So this structure maintains immutability, traceability, and also enables context-aware adaptive security. So this particular structure is very, very crucial for the next phase of our work. How does adaptive authentication work? Here's a simple analogy. Think of airport security. Some passengers get basic checks, some get extra screening, some are flagged for full security based on the threat intelligence. Air proof of authentication PoAh 2.0 works exactly the same way. Critical messages get full multi-signature validation, sensitive messages get verified by trusted regional nodes, and normal nodes are validated locally using basic cryptography. So this is encoded in algorithm 1 in our paper. The large language model and random forest models acts here like an AI-based custom officer, reading not just your documents, here is metadata, but your intent and urgency from what you say, that is contextual meaning. So metadata and contextual meaning both is really the brain of our system, and this is what gives the proof of authentication 2.0 an advantage over prior V2X blockchain security models. Let me give you a concrete example. Imagine a card sends this message: warning, sudden braking detected, suspected object on the road, visibility low. Now here is the challenge. Is this message critical? Is it just a driver mistake, or is it a false alarm from fog sensors? A conventional blockchain consensus mechanism would simply has the message, sign it, store it in the block. But it would have no idea what the message really means. An LLM understands the actual content and the context. It knows that sudden brake, along with object on the road, along with low visibility, is actually telling us something else. A strong contextual match for potential multi-vehicle collision. That is threat detection. It combines this with metadata and do behavioral analysis at high vehicle speed, traffic density. Why it is doing these things? To confirm that it is likely critical. Therefore, it triggers high assurance authentication, which ensures that this message reaches other vehicles fast and securely. And if there is no LLM, then either all the messages would get the same heavy treatment, that is adding latency, or light treatment, that is sacrificing security. Now, this is the reason LLM is essential in our architecture. It is not just a nice to have, it is important. Without it, proof of authentication could not deliver both security and latency guarantees in a privacy-preserving manner. What is the exact requirements of modern vehicle-to-everything networks? Let's do the security analysis. Why these attacks are critical to vehicle-to-everything network? Imagine you are driving a car on highway with the speed 120 kilometers, 120 kilometers per hour, and your vehicle receives a message that there is a sudden lane block 100 meters ahead. What if the message was fake, that is civil attack, or replayed from 10 minutes ago, okay, or deliberately delayed by a group of colluding malicious cars, the 51% attack. In vehicle to everything network, every millisecond matters. Unlike finance or supply chain, security here directly impacts lives. How do Sybil replay or 51% attacks work? Let me just quickly recap. Sybil attack is nothing but one malicious actor creates multiple fake identities to gain majority influence. Replay attack, it is nothing but an old but valid message is resent to mislead others. And 51% attack, if more than half of the validators are malicious, they can alter the blockchain history. So this is the another attack that we are talking about, these three attacks. These are well-known threats in blockchain, but in V2X to everything, they are more dangerous because vehicles trust messages in real time. How does proof of authentication 2.0 prevent them effectively? Here is our innovation science. Sybil attack. So here we are using actually cryptographic keys and unique MAC IDs, okay, from the vehicle. And the attacker needs to forward each digital signature correctly, and that becomes exponentially hard because 2 to the power minus L, where L is the key length, and for 256-bit ECC, the chance is less than 1 in 10 to the power 77. On the other hand, replay attack, where every transaction includes a unique transaction ID, a timestamp, a content score from our edge LLM. So here also, if an attacker reuses old message, it fails verification because 1 by 2 to the power mod h, where mod h is 256. So it's nearly impossible. And thirdly, 51% attack, where edge LLM plays a proactive role here. It continuously evaluates node behavior using anomaly detection. If several nodes start behaving oddly, their trust code drops dynamically. So it is equivalent to 1 by e to the power alpha n, where alpha is the strength of anomaly detection and n is the number of total nodes. So even with many nodes, collusion becomes near impossible unless they all pass the LLM based behavior checks. So why is this effective? Because our defense is layered and intelligent. Traditional blockchain rely only on cryptography. We add AI-based behavior analysis, transaction semantics, and context awareness via HLLM. Instead of equal treatment for all data, we prioritize critical over repeat messages, that focusing our effort where the risk is the highest. Real world deployment feasibility is very much doable in our real world setup. So the question, can it run on today's hardware? The answer is yes. We have designed PoAh 2.0 and HLM to be fully compatible with a wide range of existing automotive platforms and edge computing hardware. The framework runs efficiently on devices such as NVIDIA, Jetson, Raspberry Pi, or Qualcomm Snapdragon automotive platforms with latency well below 10 milliseconds. We have tested the same for critical transactions. This is edge native. This is another critical point, and it's not cloud native. So that's why privacy is preserved. Cities deploying smart transportation like Dubai or Singapore can implement this without redesigning their networks. It also aligns with data sovereignty laws, where vehicular data must stay within the national borders. Our next step is to move proof of authentication from simulation to large-scale V2X test beds. So do a full-scale simulation as well as go for a large-scale V2X test beds, where we can measure the real-world latency, safety, and reliability. In parallel, we are developing advanced AI models, for example, transformer-based threat detectors that sharpen anomaly detection while keeping the compute footprint light. All future upgrades will adapt privacy-preserving techniques using on-device federated fine-tuning so sensitive driver data never leaves the vehicle. We are also mapping proof authentication 2.0 to global V2X security and safety cybersecurity standards to streamline regulatory approval. Together, this effort will turn today's proof of concept into an industry solution with tangible impact on connected vehicle safety. Thank you for your time. I would like to thank all my co-authors. And if you are interested in deploying this or collaborating on this particular topic, please feel free to reach out. I would be happy to answer your questions via email. Thank you.